The benefits of implementing layered DCS in industrial control systems. Distributed control systems, DCS, are widely used in industries to monitor, control, and optimize complex processes. A layered DCS architecture provides an efficient, scalable, and organized way to manage these tasks, enhancing overall control, flexibility, and safety. In this guide, we'll walk through the basics of a DCS, the components involved, data flow, the core benefits, and some advanced functions of modern DCS technology. What is a DCS control system? A distributed control system, DCS, is a type of industrial control system that monitors and controls large, complex processes, often in manufacturing, energy production, or chemical processing. Unlike centralized control systems, a DCS spreads control functions across multiple layers, providing a robust and decentralized structure that enhances both flexibility and reliability. DCS control systems employ a layered architecture where tasks and functions are distributed across various levels, enabling better control, monitoring, and data management. This approach divides the system into manageable segments and helps ensure that each layer is specialized in a particular set of functions. Basic components of a DCS. A DCS typically consists of three main components, each fulfilling a critical role in the control and monitoring process. 1. Controllers. Controllers are responsible for processing data from the sensors and generating control signals. They perform calculations, interpret inputs, and ensure the process is running as intended. 2. PLCs, programmable logic controllers. PLCs manage logic operations and directly control specific equipment. They're designed for high-speed, real-time decision-making and handle tasks such as activating or deactivating machinery based on set parameters. Number 3, HMIs, human-machine interfaces. HMIs allow operators to interact with the system and view real-time information about the process. Through the HMI, operators can adjust parameters, monitor system health, and receive alerts when something goes awry. Data flow in a DCS. The data flow in a DCS is structured to ensure seamless monitoring and control. Data collection. Sensors throughout the process feed real-time data into the controllers. This data might include temperature, pressure, flow rates, or any variable relevant to the process. Processing. Controllers analyze this data, process it according to preset parameters, and make decisions based on the current conditions. Control signal generation. The process data is translated into control signals which are sent to actuators and other control devices. Execution. Actuators adjust physical variables like valve positions or motor speeds based on the control signals, effectively maintaining the desired operational parameters. Benefits of implementing a layered DCS. Implementing a layered DCS provides several advantages, making it an ideal choice for modern industrial operations. 1. Improved efficiency and safety. A layered DCS structure streamlines operations and reduces human error by automating repetitive tasks. By maintaining real-time monitoring, the system can immediately respond to deviations from the norm, triggering alarms or taking corrective actions to ensure safe operation. This automation helps prevent accidents and equipment failures, ensuring a safe working environment. 2. Enhanced cost savings and profitability. Layered DCS systems optimize resource usage and reduce energy consumption by precisely controlling each part of the process. Fewer manual interventions are required, reducing labor costs. Additionally, early detection of inefficiencies and issues means that equipment can be serviced before more costly repairs are needed, contributing to better cost management and higher profitability. 3. Improved quality of products and services. By maintaining consistent process parameters, DCS systems help ensure product quality. Precise control over variables like temperature, pressure, and flow means that each batch or unit produced meets the required specifications. This results in higher product quality and reduces waste, ultimately benefiting both the producer and the end consumer. 4. Scalability and flexibility. A layered DCS architecture is inherently modular, meaning that new layers, controllers, or functionalities can be added as the system grows. This makes it easy to scale the system over time, adapting to increased production needs or incorporating advanced functions. This modularity allows facilities to adapt quickly to market demands or process changes. 5. Centralized monitoring and control. Even though a DCS is decentralized, a layered architecture enables centralized monitoring and control via HMIs. Operators have full visibility of the entire process from a single location, allowing them to make informed decisions quickly. This unified view is essential for large, complex processes where multiple variables must be monitored simultaneously. Advanced functions of a modern-day DCS. Modern DCS systems go beyond basic monitoring and control. Today's advanced DCS technology incorporates several high-level functions that enhance efficiency, safety, and decision-making. Data analytics and predictive maintenance. Many modern DCS systems now include analytics capabilities that allow operators to predict when maintenance is needed. By analyzing data trends, the system can forecast equipment wear and potential failures, reducing unplanned downtime and improving maintenance schedules. Process optimization and advanced control. Advanced DCS systems can perform sophisticated calculations and optimizations in real time, adapting control strategies to maximize output while minimizing resource usage. This function enables the DCS to respond dynamically to changing conditions, such as fluctuating demand or variations in raw materials. Cybersecurity and remote access. Modern DCS systems incorporate advanced cybersecurity measures to protect against unauthorized access or cyber threats. With secure remote access capabilities, operators and engineers can monitor and adjust processes from remote locations, which is particularly useful for distributed facilities or during emergencies. Integration with other systems. Advanced DCS systems can seamlessly integrate with other digital systems such as enterprise resource planning, ERP, or manufacturing execution systems, MES. This integration allows for real-time data sharing across departments, enabling more coordinated operations and better informed decision-making. Conclusion: the value of layered DCS for engineers. Implementing a layered DCS system offers a range of benefits that enhance process safety, efficiency, quality, and flexibility. By dividing control tasks across multiple layers, a layered DCS provides an organized, modular, and scalable approach to industrial process management. From core functions like data processing and real-time control to advanced features like predictive maintenance and remote access, a modern DCS supports engineers in building reliable, safe, and adaptable systems. For industrial facilities looking to optimize their processes and remain competitive, a layered DCS is an invaluable asset. With the benefits of improved safety, cost savings, product quality, and scalability, implementing a layered DCS is a step toward a smarter, more resilient operation. Practical examples of layered control implementation in upstream oil and gas. In the upstream oil and gas industry, layered control systems are essential for ensuring safety, efficiency, and reliability in complex processes like drilling, extraction, and well management. Implementing a layered distributed control system, DCS, in this industry provides multiple levels of control that help operators maintain optimal production rates while protecting personnel, equipment, and the environment. Here are some practical examples of how layered control can be applied in upstream oil and gas operations. 1. Wellhead control and monitoring. In upstream operations, the wellhead is one of the most critical components, managing the flow of oil and gas from the reservoir to the surface. A layered DCS in wellhead control provides distinct levels of monitoring and control for safe, efficient operation. Primary control layer. This layer handles basic operations such as controlling the pressure, temperature, and flow rate at the wellhead to ensure stable output. Programmable logic controllers, PLCs, monitor and adjust the valves and chokes in real time to maintain optimal conditions. Safety layer. The safety layer includes emergency shutdown, ESD systems, which automatically shut down the wellhead in the event of high pressure, over temperature, or leakage. If primary controls detect a dangerous deviation, the ESD system can immediately isolate the well to prevent blowouts or other hazardous situations. Remote monitoring and data layer. Operators can remotely monitor wellhead data through an HMI, human-machine interface, or supervisory control system, allowing engineers to make adjustments or investigate alarms without needing to be on site. This layer provides real-time data analytics for trend analysis and predictive maintenance. 2. Gas compression and separation. Gas compression and separation are critical in preparing raw hydrocarbons for transportation and refining. Layered DCS control and gas compression allows for precise control and safe operation of equipment like compressors, separators, and pumps. Basic process control layer. This layer focuses on maintaining stable pressure and flow rates through compressors and separators. PLCs control the compressor speed and adjust separator parameters to achieve the desired separation between oil, gas, and water. Secondary control layer, surge protection. Compressors are susceptible to surges, which can lead to equipment damage. A secondary control layer constantly monitors for surge conditions and adjusts the inlet or outlet flows to prevent compressor surge, ensuring continuous, reliable operation. Emergency shutdown layer. If the compression or separation process encounters an abnormal condition like excessive pressure, the ESD layer shuts down the compressor and closes isolation valves to prevent any accidents. This layer is crucial for protecting equipment and personnel from potentially explosive situations. Remote and predictive analytics layer. Remote monitoring with advanced analytics allows operators to track key performance indicators, KPIs, like compressor efficiency, vibration levels, and temperature trends. By leveraging predictive maintenance, this layer helps forecast issues, reducing unplanned downtime. However, 3. Artificial lift systems. Artificial lift systems, such as electric submersible pumps, ESPs, and gas lift, are widely used to enhance oil production from wells with insufficient natural pressure. Layered control in these systems optimizes pump performance while protecting against equipment failure. Operational control layer. The basic control layer handles pump speed adjustments to achieve the desired production rate. For gas lift systems, this layer manages gas injection rates to optimize flow. Equipment protection layer. An intermediate layer continuously monitors variables like pump vibration, temperature, and downhole pressure. If abnormal conditions arise, such as high vibration or over temperature, the system adjusts pump speed or injection rates to prevent damage. Emergency shutdown layer. To protect against failures that could damage the well or the pump, the ESD system can shut down the ESP or gas lift if critical conditions are detected. This layer also includes automated alarms to alert operators if the pump is operating outside safe parameters. Data and analytics layer. By collecting data from downhole sensors, the analytics layer provides insights into well performance, allowing engineers to adjust artificial lift parameters based on real-time well conditions. Predictive maintenance models use this data to predict equipment wear and schedule maintenance proactively. 4. Drilling operations. Drilling is one of the most complex and high-risk activities in upstream oil and gas. Layered control systems ensure that drilling operations proceed safely and efficiently by managing pressures, drill speeds, and drilling fluids. Primary drilling control layer. The basic control layer regulates drill speed, weight on bit, and drilling fluid circulation to ensure stable operation and maximum penetration rates. Automated systems make real-time adjustments based on downhole conditions to keep drilling optimized. Blowout prevention layer. In drilling, managing pressure to avoid blowouts is essential. This layer continuously monitors wellbore pressure and activates blowout preventers, BOPs, when pressure thresholds are exceeded. The BOP system closes the well in emergencies to prevent uncontrolled hydrocarbon releases. Hydraulics and fluid management layer. A separate layer oversees the drilling fluid, mud properties to maintain the right density and viscosity, preventing formation collapse or wellbore instability. PLCs adjust mud pumps to keep up with required circulation rates based on real-time data. Data integration and monitoring layer. Data from downhole sensors, drilling logs, and mud logging systems are integrated into a supervisory control system for real-time decision-making. Engineers can analyze this data to optimize drilling parameters or detect issues like kick events where formation fluid flows into the wellbore. 5. Pipeline monitoring and leak detection. Pipelines are critical for transporting oil and gas from extraction sites to processing facilities, and a layered control system provides robust monitoring and emergency response capabilities. Flow and pressure control layer. The primary control layer monitors flow rates and pressures to maintain efficient pipeline transport. Controllers adjust pump speeds or valve positions to ensure that flow remains within desired limits. Leak detection layer. A secondary layer uses specialized leak detection algorithms and sensors to monitor for signs of leaks, such as pressure drops or gas presence in pipeline sections. This layer can identify small leaks early, enabling prompt response before they escalate into significant issues. Isolation and shutdown layer. If a leak is detected, the ESD system isolates affected sections by closing valves and stopping pumps. This emergency layer is essential for minimizing environmental impact and preventing product loss. Remote monitoring and analytics layer. Advanced systems provide operators with real-time data on pipeline integrity, allowing for remote monitoring and predictive analytics. This layer includes alarm systems that alert operators to irregularities, improving response times and decision-making.